Good morrow, fellow humans. My name is Sean Crowley and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is. In the last chapter, we discussed the biological self and the subjective borders that we place on the physical universe in order to understand our concepts of I and self. And so that's the story, or at least it would have been up until the beginning of the 20th century, when, on closer inspection, it was discovered that those atomic bodies, those that shape this physical self, didn't appear to have a determinable existence for the most part anyway. So now may be the time for us to have that cheeky peek into the bizarre headspace we call quantum physics. For a century now, quantum physics has continued to challenge our understanding of this physical self, with few ideas more confronting than quantum superposition, a trait inherent to all quantum objects. It suggests an ability to exist in multiple states at the same time. As mentioned in prior chapters, the electrons of our atoms fly, sort of, around, again, sort of, the nucleus of the atom. But due to this nature of superposition, a more accurate description should clarify that neither the electrons nor the nucleus hold any particular location in either space or time, that is, until they are determined by an observer. As said, when envisioning quantum objects, it's often best to imagine them as hosting attributes more closely aligned with clouds rather than billiard balls, as quantum objects require both wave-like and particle-like qualities in order to describe their fundamental nature. But unlike clouds in the sky, a quantum object's cloud state is one of probability. The dynamics of this probability are given to us by the Schrödinger equation, a mathematical description of the wave function correlating with how likely it is that a particle will be found within any region of space. So if it is highly probable that a particle will be found within a particular location, then the wave function is also considered high. If improbable, then the wave function is low. And it is this wave of varying probability that is said to exist across the space where we first imagined our cloud to be. However, once we observe the object via measurement, we can temporarily gain an almost certain degree of knowledge concerning its location or momentum. When this happens, we say that the probability wave has collapsed. But whilst it remains unobserved, it is said to exist in a fluxing state of many positions, a superposition. The second half of this conundrum is the Heisenberg uncertainty principle, an equally important equation in the world of quantum mechanics that describes how the limits of this knowledge teeter atop a seesaw of uncertainty, forbidding us from ever attaining a quantum object's location and momentum simultaneously. A quantum wavelength, determined by an object's energy, is like any other wave. No matter how short, it is always stretched out in space and time. Thus, the problems associated with wave-particle duality are highlighted since the location is primarily determined via its particle-like quality, whereas momentum is derived from its wave-like quality. So, like any ordinary photograph, as we focus on the freeze frame of location, it's clear how we always lose information regarding motion. Only when we stretch our measurement across a period of time, like with a movie, can we regain this information. Though, like the movie, though we attain motion, our knowledge of location between any two frames is entirely unknowable. Though it was Werner Heisenberg's 1927 equation that gave us an understanding of how this probability wave behaves, His initial intention was to describe the limitations of classical measurement. Classical meaning pre-quantum mechanics, i.e., things tend to stay where they're told. The principal problem, as Heisenberg saw it, was that to measure a particle's position with higher and higher accuracy, we must focus a wave of light into smaller and smaller wavelengths, i.e., higher frequencies. This is the quantum equivalent of looking at something. But with these ever-increasing frequencies will always come higher and higher energies, thus making it increasingly difficult not to affect the particle's momentum. The energies just kick the particle further along. Indeed, by the time we have reached an accuracy equivalent to Planck's constant, we have precisely zero knowledge concerning its momentum. This is our point of no return, a limit where neither location nor speed can have any meaning whatsoever, and thus the finest possible scale of quanta and measurement. But as we lower or widen our frequencies to achieve those desired subtler interactions, we inevitably start to forfeit any accuracy we had of its location. This, he proposed, was the observer effect. But it was Heisenberg's friend, mentor and collaborator Niels Bohr who, shortly after the equation's publication, endeavoured to push these findings beyond a description of mere knowledge, suggesting the presence of a far more important insight. An insight that was not only fundamental to the nature of the particle, but physicality itself. According to Bohr, not only should we have conflicting confidence in our knowledge of a quantum object's whereabouts, but this balancing act of uncertainty must also be true of its actuality. Because though both the waviness of its momentum and the particleness of its position appear necessary to describe the object, neither attribute should ever be considered an ultimate hierarchical quality of its nature. According to Bohr and the most widely taught interpretations of quantum mechanics today, it's not that we don't know where the particle is, it's that it literally does not have a location until observed. Prior to our knowing, it is said to exist in part everywhere, or at least everywhere where the wave function suggests a non-zero potential for existence. So, yeah, everywhere. An infinite superposition of locations. But this is not because it is some magical particle. It's because it's not a particle, nor is it a wave. Not really. Such claims can be dangerous, since we're all at the whim of our own subjective interpretation, and so without a mathematical understanding of what is essentially a mathematical idea, it's very easy to be misled. The truth is, we don't know, and possibly cannot know what's happening during the particle's wave state. All we know is that the equations correspond with measurement to an incredibly high accuracy. Thus, the interpretations have been wild and many, plenty of which we shall discuss in later chapters. However, it should be said that to date, no interpretation that has ever wished to force our once conventional ideals of deterministic realism back into the picture has ever successfully managed to do so without calling back onto the stage a whole suite of quantum peculiarities. Conceived by Erwin Schrödinger in 1935, the famous Shröedingers Cat thought experiment was initially devised to prove just how paradoxical this whole situation was. In it, Schrödinger proposed a device that would either withhold or release a vial of poison depending on the random decay of a quantum particle. But because this particle is thought to remain in a superposition of both states until observed, the poison should also be both released and withheld until observed. This means that if we were to place this contraption into a closed box with a cat, clearly Erwin was more of a dog man, then the cat too would be in a superposition of both dead and alive until observed. though I have always been curious as to what the cat might have to say about all this. Even so, nowadays, this thought experiment is more often used to highlight the peculiarity of superposition, rather than deny its existence as originally intended. And so, if you are left somewhat baffled by all of this, please do not stress, as even the most outstanding physicists of all time have enjoyed brandishing the phrase, "If you think you understand quantum physics, then you don't understand quantum physics." But let's not allow that to slow us down. Let us see if we can fail to understand things in a little more detail. The following thought experiment, often given to first-year physics students, is one that attempts to show how superposition works in practice. Now, imagine we have 3 boxes, A, B, and C. The first, labelled A, has a single input and 2 outputs connecting it with box B. B also has 2 outputs connected to C, which itself has the 2 final outputs. Each box has the ability to measure and divide particles into 2 groups, reflecting some underlying binary quality. This could be up-down, on-off, hot-cold. It doesn't really matter. What does matter is that there are always 2 completely unrelated binary choices. In practice, this could be the spin of an electron or the polarization of a photon, but for our purposes, box A and C will simply measure the binary state of black or white, and box B will measure hard and soft. All this means is that if we fire one black particle into box A, it will always exit via the black output. One hard particle goes into B, and one hard particle exits via the hard output. That's it. These boxes measure and divide and nothing else. Okay, so first, let's fire a collection of 1,000 particles into box A, currently set to measure the particle state of either black or white. Upon doing this, we find an average 50-50 split, 500 white and 500 black particles. Now say that we close the white output and only allow the black particles to pass into box B. We can now measure the balance of hard and soft among these. When we do, our experiment again finds another average 50-50 split, 250 hard particles and 250 soft. But here is where things get a little more fun. Because when we close one of B's outputs and only allow for these 250 hard black particles to pass into box C, again set to measure black or white, what we find is that instead of all 250 still being black as one would assume, they have somehow split into that original 50-50 ratio, now appearing to be 125 black and 125 white. What seems to have happened is that by measuring the hardness state, we somehow changed these black particles into a mix of both black and white. Now this may already appear odd, but with further probing, things become, well, odder. So let's rerun the experiment. First passing our 1,000 particles into box A, and as before, allowing only the 500 black particles into box B's hardness reader. But this time, once all 500 have had their hardness determined, we don't block any further paths. Instead, we allow all hard and soft particles to enter box C. And this time, we see that the final output has remained in its original state of 100% black. Allowing our particles to have had their hardness determined has had no effect on the shade this time. But why? What was different? The difference is that we don't know which of the 2 hardness options any individual particle was as it entered box C, since both hard and soft particles were allowed to enter the final reading. Therefore, it can no longer be determined which are hard and which are soft. That information has been destroyed. And so it wasn't the act of measuring hard or soft after all. It was the act of retaining the hard or soft information that determined whether or not our first set of measurements remained true. So whenever we block one of B's two hardness ports, the final 50-50 split of black and white resumes at C. We remove the block 100% black. Once we know one attribute, we cannot know the other. It is simply impossible to learn both at the same time. But we can now probe this experiment a little further. Based on our current test results, which said that a determined path of hardness will always give us uncertainty regarding shade, we can ask, which of the two outputs, hard or soft, did particles pass through in the second experiment? Because though we may not ever know the answer, there must still be one. However, we know it can't be as simple as the hard using the hard output or the soft using the soft, because, as we said, a determined path of hardness always gives us uncertainty regarding shade. If it was an ordinary determined path, we should find that 50-50 split of black and white resuming. So, what could be happening? Maybe the particles are somehow going down both routes at the same time. The problem with that is that when we check, we only ever see full particles, never half particles. Okay, so what if the particles mysteriously bypassed the hardness box altogether, drifting outside of our experiment somehow? Well, if we close both outputs, no particles arrive at all, so that doesn't appear to be the answer either. The only answer we can give is that when we don't measure the particle's hardness state, it remains in a superposition of hard, soft, and neither all at once. But when we do measure the hardness, it collapses into that observed state, removing any determinability of the particle's shade. But it is important to note that this is not an issue with our measuring device, nor is it to be confused with the original observer effect problem that Heisenberg answered. According to many, these contrary results are the reflection of an uncertainty that is of the quantum object's very nature. But don't take my word for it, as you can run this same test yourself with only 3 pairs of polarized sunglasses. The way that polarized glasses work is that they only allow for the vertical rays of light to pass through, blocking those that fall horizontal to your face. An act that gives us knowledge about a quantum particle state, i.e. whether its wavelength was horizontal or vertically aligned. This is yet another example of a binary quantum question. And so, if we have one set of glasses, we block all vertical light, darkening the light that passes through, add a second pair and lay it perpendicular to the first, and we now block all horizontal waves, darkening the light almost completely. But add a third in between these two at a diagonal angle, and thus asking a second binary question. And we can no longer know which photons entered the first pair of sunglasses at vertical or horizontal angles. Meaning that by adding the third pair of sunglasses between the first two, we start to see the light paradoxically increase in brightness. And so, in relation to our original cloud that was said to surround the nucleus, this undetermined state is like the one that we described earlier, where there is an undetermined potential for an electron to be found in this or that space at any one time. The nature of an electron is to exist in a wave-like superposition across the entire area of the atom until physically measured, allowing it to then say, "Oh, here I am." In fact, it is this quality of superposition that binds atoms together, allowing them to form the higher molecules. The reason why the 2 oxygen atoms of an O2 oxygen molecule stick together is because they share an electron bound in superposition, existing in both of the 2 atoms at the same time. And budding physicists are all taught to interpret this quite literally. that the particle exists in a state of particle-wave duality. However, it's essential to understand that particle-wave duality isn't an entirely accurate title, because it isn't that the electron is both a particle and a wave, because it doesn't have to be either. More accurately, it's neither, for it is something else. It is something that has the attributes of either a particle or a wave, depending on how we look at it. It is a dance that is as equal in its being as it is in its becoming. Things can get even more complicated when we consider another bizarre pillar of quantum mechanics, entanglement. We will come back to this lovely little head melt in later chapters, but for now, remember that none of this weirdness is happening due to our technical inability to measure such smaller happenings. And therefore, these peculiarities are just as relevant when describing the nature of our own physicality. But way, way, way back, at our more familiar macro scale of existence, where our body's own wave properties are so tiny that they're negligible, we can be happy enough to agree that, for the most part, our matter remains where we left it. Yes, reality might be non-deterministic and hazy at the scale of the very, very small, but this doesn't negate the validity of the classical physics we experience at the macro scale. Again, these are equal yet contradictory truths that reflect our underlying reality. To state that I am here or that I am only here when I am observed could both be equally accurate. A contradiction does not require one perspective to be considered an illusion. More likely, this hints at the limitations of our perspective, in part true, whilst eternally and infinitely incomplete. But after all of that, after the last few chapters and the many turning over of rocks in search for this physical self, it turns out that there are, in fact, a few human cells that, unlike most of our body, do hang about for the length of a lifetime. So can we call these cells an I, if only temporarily? The heart muscles will only be partially replaced over one's lifetime, leaving about half our heart in its original pre-birth cell arrangement. The inner lens of each eye, our tooth enamel, all stay with us for life. And most intriguingly of all, the cerebral cortex. The cerebral cortex, often referred to as the brain's grey matter, is the major outer mass surrounding the cerebellum. Present in our body even before its birth, it is also the most complex part of the brain, understood to be responsible for creating, understanding, perceiving. In fact, most higher cognitive processing happens here. Some part of our brain, such as the hippocampus, responsible for memory, do replace cells over time, but the cerebral cortex is essentially with you for life. Maybe the I that we seek lives here. Thank you so much for tuning in again. I'm so glad that everyone has been enjoying the chapters thus far and really getting involved in the comment section. It's been lovely to chat with you. Just before you go, because this week's episode did have some more technical elements in it, I just wanted to let you know that next week we will be uploading a visualization to this episode, as we do every week. This visualization, however, will have a special animation that's been created by a good friend of mine, Callum Wilcock, just to help us all try and imagine what it is we're talking about when we're discussing that 3-box thought experiment. But otherwise, much love, and I hope you all have a wonderful, wonderful week. All right, see you later. Bye.